Okay.
So I'm giving kind of a higher level, but a little bit more specific overview of the architecture of LLVM. Sorry, previous talks have been kind of discussing research papers. This is more of just like a kind of a high-level design. If you were to build a compilation pipeline, what is an example of one of the production systems that we use quite extensively throughout Google look like? Take everything I'm going to show you today with a grain of salt. I'm not an expert on this. I've only been working on it for almost 2 years, kind of thing. So this hasn't been vetted by people way more senior than me. It could be wrong, right? But generally, this is kind of my understanding of the world. So just double checking that I'm sharing the tab correctly. Other folks can see it. Thumbs up. Yeah. Okay. So this was there's a excellent book series. There are 3 of these books, but this diagram kind of shamelessly stolen from. There's this book called The Architecture of Open Source, and each chapter is written by a different author about from a different open source project. There's like a chapter on Ninja and all about the architecture of Ninja. This is taken from the LLVM chapter. So I think some of the chapters are free online. So I recommend go read it. It's pretty old at this point and it's not super accurate, but this is kind of the general idea, right? Is when building a compiler, right? It would be kind of nice if we could centralize all the classical compiler optimizations that aren't really language dependent or aren't really target dependent, kind of the backend part, and have that be like a core set of libraries that's reusable, right? And that's kind of the core idea behind LLVM's optimizer. And we're seeing kind of similar things a little bit with MLIR, but I'm not really going to get into that today. So the idea is basically if you have some kind of intermediary representation, what I'll call IR from now on, that's more general, you can kind of have multiple different language front ends emit this, and then be able to reuse these optimizations on this kind of meta high-level language or IR, and then from there, you can feed that off to a different backend and generate code. And this makes it really easy if you want to either create a new language and not have to worry about classical compiler optimizations or machine-specific code generation by just having your front end emit LLVM IR. So a lot of new languages like Zig or Rust or Swift all kind of emit LLVM IR, and then LLVM takes over from there. Clang is a front end that handles C, C++, the objective C and C++, OpenMP, I think CUDA kind of translates these all to LLVM IR. And there's actually kind of more to these equations, right? So I'm going to get into more in depth with the architecture. So let me flip tabs to a little bit better view. Can folks see this? The new thing? Okay. So the idea here, basically, this is the front end of Clang. If we zoom in, kind of, pinch and zoom a little bit at the architecture, let's see what's going on here. And I kind of, the whole thing to me is one big pipeline kind of thing. But it gets a little bit more complicated than that. We'll see in a little bit, right? So kind of as input to this whole process, we have, whatever source language that the human wrote, the machine doesn't understand it, right? Unless someone has an interpreter for it. So, we want to generate at the end of the day, the machine specific code, but instead for a front end, we're more concerned with kind of outputting LLVM IR. So kind of the first step in Clang, and you'll have to forgive me, I have a lot of kind of source files in here. You'll see these .cpp. This is more for like if a beginner is interested in understanding like where in the source tree is this done, right? So a common theme when getting started in a new code base is like, I know the general overall idea, but like where is it implemented? So, I kind of have the paths to the source trees. If you were to clone LLVM project off GitHub, you could go and take a look and like read through these implementations. And, I find the interfaces for these objects really helpful in understanding, what is the core responsibility of each of these classes, right? So the first thing we do is we kind of pre-process, do the job of the C preprocessor, right? Kind of expanding macros, including other source files kind of thing. The Lexer breaks up all the individual characters into tokens. From there, we do parsing. So we want to convert those tokens into an abstract syntax tree. So the act of parsing and constructing an AST are kind of two separate ideas, and there is some type inference that actually occurs at this level. So most cases of C++'s keyword auto is actually instantiated at parsing time. So there's some type inference that occurs there. From there, within Clang, semantic analysis and template instantiation and more type inference is kind of done. So semantic analysis is really the brunt of, we want to try to find mistakes that a programmer has made, either things that may lead to bugs that we might want to warn them about, or things where we're not going to be able to generate valid code. This is ambiguous or not valid code, and they're compiler errors, right? So Clang emits what we call diagnostics, which can be either warnings or errors, and you can flip flags around to set one or another. Some things are always hard errors, but the template instantiation ends up basically cloning parts of the AST, but kind of specialized for specific types. And then there's also type inference that has to be done for templates, right? So they have different type deduction rules than the auto keyword does in C++. And for decal type, I don't remember if decal type, I think it's done in this later phase. I could be wrong there. Then the final part is emitting the LLVM IR. And so in Clang's idea of code gen is not targeting machine code, it's targeting LLVM IR. And it basically just does an AST walk. And Clang has the ability to construct a control flow graph, and it does so for some semantic analysis, but it's considered both heavyweight and it's not used today as part of code gen. Sometimes we construct delayed diagnostics where if we do any optimizations in Clang and we delete the AST node, the corresponding diagnostic doesn't get emitted, kind of thing. One of the things that's different between GCC and Clang is Clang does all the semantic analysis up front. GCC will do early inlining and dead code elimination. So you can have syntax errors in dead code in GCC and it will not warn you. Clang, it will. It's kind of a very obvious thing that I run to a lot. So from here, let's take a look at what the IR kind of looks like in LLVM from a class perspective. So let me zoom in on this. So the idea in LLVM at the IR level is there's kind of 4 real classes that encapsulate one another, like Matryoshka stacking dolls, right? Is kind of, there's a class LLVM module, is you can think of it like a translation unit, but it's a little bit more generic. When you do LTO, everything's in one module. It's kind of, the world as the compiler understands it. From there, a module contains one-to-many functions, right? Just like you would in C. So, C++ classes actually get boiled down in, it's just syntactic sugar and scoping for a bunch of functions, right? Get broken down into functions. From there, functions contain basic blocks. Basic blocks are basically straight line sequences of statements that get terminated on control flow. Like branches, if statements, for loops, any kind of edge in a graph, you might kind of links these basic blocks together. And then finally, so a function can have one-to-many basic blocks, and then finally a basic block can have one-to-many instructions, right? So, and I'll show you in a little bit kind of what the LLVM IR looks like kind of thing, but this is, very high level, and in even later passes in LLVM IR kind of keep a very similar kind of structure. So now if we zoom in on the back end here, so within LLVM, kind of in the source tree, there's a top level directory called LLVM. It actually has kind of both the middle end, the IR optimizations that are generic, like not specific to a machine, but then the back end itself, which is machine specific, are both within the same directory, but they're kind of two concise units, right? So opt is a collection of that takes in LLVM IR and emits LLVM IR. And this is like kind of very classical compiler optimizations live here. A lot of the passes aren't really dependent on one another and can be run in any order. And the IR should be able to be fed from one pass into another in most cases. So a lot of the passes in here are broken up into both analyses and transforms, and then sometimes utilities. So there's a lot of transforms depend on certain analyses, but the transforms themselves are destructive. So basically, if you compute some kind of expensive analysis, like what is the cost of inlining this function into another, and then you actually go ahead and inline something, kind of the previous analysis you've done may now be invalidated. So there's this thing in LLVM called the new pass manager. Passes can be chained in pipelines, and then you can repeat pipelines. You can have multiple pipelines. You can have, just sequences of passes. But there's a way in LLVM for you to say, like, my transform is destructive. It invalidates these analyses, or it requires these analyses to be run, right? So for instance, the inliner is broken up into mostly 3 pieces. There's actually a couple more, but the really important ones, there's the inline cost analysis, which kind of says, like, should I and could I inline this? Transform, the inliner, is what actually makes the decision, kind of based on those distilled signals. And then in-utils inline function has a bunch of helper functions that will actually do the code transformations and cleanup. It doesn't know better. If you tell it to inline it, it's going to inline it, and even if it's not profitable enough. So kind of the transforms what is like driving making decisions based on what it's been told by the analyses. And there's a whole bunch in here. I don't go through them, but we'll go through and see a list of them in a little bit. From once we kind of leave the middle end and we're in the back end, we're focused on code gen, and there's kind of a collection of passes that are both machine generic, which live in a certain part of the tree, and machine specific, and they work together. And it's very common in LLVM. It's a C++ code base. It's very common for the generic classes to be a base class, and then to have machine specific derived classes. And the machine specific derived classes will typically override the base class and either do something very specific to that target architecture, or call into the base class. If they don't have to do anything special, they may do both. Is very common as well. So it kind of takes an LLVM IR, and then, as we'll see, we go through 2 other actual IRs within LLVM, and they get kind of machine and pass specific. So they're not as nice as opt, where you can mix and match passes however you please. They kind of get ordering dependent, which is, makes them a little bit harder to work with. But and there's kind of multiple passes. The only 2 I'm going to cover are instruction selection and register allocation, are kind of the 2 largest ones and most important ones in my opinion. They're not actually required at all when writing a backend for LLVM. Technically, the only classes required for a backend are specifying the target machine, such as maybe what the CPU is really kind of describing roughly what you're targeting, and the data layout, which is really like, what's your data model? What's the size of a pointer? Are you ILP32 or LP64? Or, do you support long double? And what the hell does that look like? And kind of things like that. So LLVM used to have a C backend. It could generate C code. So it only requires those 2 classes, though C backend's been removed, and I don't know if this is still true anymore, but instruction selection is kind of the big one. And LLVM has 3 instruction selectors that it uses in the tree. And selection DAG is kind of like the workhorse. It actually converts the IR out of SSA form into a directed acyclic graph, and tries to do kind of pattern matching on it. It's very old, but it's the most well tested, kind of the best thing if you want full optimization. Selection DAG is the go-to. A lot of slowdown in LLVM, I suspect, comes from selection DAG. Since then, people have written 2 other instruction selectors. Moving to them is a lot of work. So fast ICEL is for the case where you care more about compilation speed. You don't really care about performing every optimization or as many aggressive optimizations during instruction selection. Can generate code very fast. And since then, global ICEL has been like a newer instruction selector. I think our AR64 backend uses it in place of fast ICEL, but it's still a work in progress, moving the various targets kind of to it. It tries to keep the same SSA form and not waste time converting back and forth from SSA to DAG back to SSA. But it's still a work in progress and has been for a very long time. So there are 3 different instruction selectors in LLVM, where selection DAG is kind of the base one. And even if fast ICEL and global ICEL, don't really know what to do in a particular case, they will fall back to selection DAG. they'll bail out kind of thing. But kind of once we're done with instruction selection, the output of it is a whole new IR. It's a different class in LLVM. Instead of LLVM instruction, it's LLVM machine inster. People sometimes refer to this as mirror, the machine IR. And machine IR begins to start to look a little bit like assembly. There's like, instead of having operations that are from LLVM land, they are more machine specific at this point, but some of them are very generic. Some are kind of high level or pseudo operations that will eventually be expanded into multiple instructions at the end of the day. And kind of the big thing with the mirror class is, because we haven't done register allocation yet, the operands to it are a mix of virtual and physical registers, right? So before we do register allocation, we kind of pretend we're targeting a abstract machine that has infinite virtual registers. And eventually when we get to register allocation, we're going to say, well, a concrete machine doesn't have infinite registers. So we need to either allocate them to physical registers or emit spills to the stack in reloads. And the thing with mirror is, actually after instruction selection, sometimes there will be concrete physical registers. And the cases where there are concrete physical registers are when the calling convention of the ABI that you're targeting require it. So kind of it's like RDI, RSI, RDX, whatever, like your C calling convention, for instance. If you have register variables that are allocated to specific physical registers, if you have extended inline assembly that has outputs with constraints that say it must go in this physical register, kind of at that point, post ICEL pre-register allocation, that's when we have this mix of virtual and physical registers, right? And there are many passes kind of before ICEL. There's many passes after ICEL. For instance, we do instruction scheduling before register allocation. We actually do another form of instruction scheduling after register allocation as well. But when it comes to register allocation, LLVM has 4 different register allocators. And again, it can depend on, what target architecture you're targeting and what optimization level you're targeting, right? So for instance, when I'm targeting x86 and turning on, compiling 4 optimizations, maybe O2, regalloc greedy, the greedy register allocator is what's run. There's a fast register allocator if you care more about compile times. There's kind of a basic one. I don't know if it's really used. Greedy is actually derived from the basic register allocator. This header is interesting. This regalloc basic actually defines the interface for which all register allocators need to kind of, define define themselves against. But essentially, after register allocation, we should not have any more virtual registers. We should only have concrete registers or spills in reloads from the stack. So we still have we're still at the mirror level after regalloc, bunch of passes as well. Finally, we get to a class that I guess is claimed it's been misnamed. It's called ASM printer. But at this point, we now convert to the final IR in LLVM. Class called MC inst. Some people call this the MC layer. At this point, you have like a one-to-one mapping between an object in like a C++ object in memory to an instruction, an actual like machine assembler mnemonic or instruction that will be emitted, kind of thing. So ASM printer's job is kind of take this abstract high-level assembly-like language and like really straighten it out and really get it in ready for code gen. So now from here, the MC layer major component of it is the MC streamer class, is a base class, and there's 2 major subclasses that are really, really important to it. So most of the time when we're compiling, we want to generate machine-specific code. We want to generate object files, and we want to wrap those object files that are, we've kind of encoded our instructions. Like ASM printer will now, MC streamer is what's in charge of like, when I see an assembler, it's almost like an assembler, right? It's like, for an instruction, generate the bit pattern and the encoding for this instruction that the machine wants, right? And there's kind of child classes of that. There's MC-ELF streamer, Mach-O streamer, WinCoff streamer, WASM streamer, and these will output, kind of object files wrapped in whatever object file format you're targeting based on your target machine or ABI. Conversely, if you want to, say, disassemble, or you want to generate assembly, instead MC-ASM streamer is used, and it's basically just calls printf on a buffered stream. That's like literally its design. And it will emit the assembly code. So inline assembly is generally treated as a black box through LLVM. All the way through. MC-ASM streamer will call if you have like format specifiers, literally just printf tricks. Some interesting classes to take a look at in LLVM are target register info and target inster info. Basically, they describe for a specific machine, what does the registers look like? And they're actually written in this high-level meta language in LLVM called TableGen. It's like C++ templates on crack. It's kind of a descriptive way instead of a imperative way of describing things that you may have a lot of and you kind of want to generate definitions for. So for instance, I don't want to generate encodings for every possible instruction in x86. Instead, what can I parameterize here? And what can I generate definitions for? So TableGen will take in these TD files. It'll generate a .inc file that's valid C++. That will get pound included by the C preprocessor into typically headers in LLVM during the build of LLVM itself. And then those headers get included in various C++ objects, which can then extend them further or do things with them. So register info kind of describes what are the registers of my machine, and they can differ between extensions to ISAs, typically add registers, for instance. But then target inster info will also define what are all the what are all the instructions as well in my ISA or extensions of the ISA. The idea behind LLVM more generally is that it's very common in the GNU world or C in general to have lots of little library shared objects that you all link together. And LLVM kind of says, well, why don't we make C++ classes for all these and then reuse them to build a compiler, but also like a disassembler and obj copy and everything in bin utils. And kind of makes it very, very easy to reuse. So that's kind of the high-level architecture of LLVM. Now I just want to give you a quick overview of how, one of the things I appreciate about LLVM is that I find it very easy when debugging it. The abilities that it provides for introspection of, I suspect there's a compiler bug. Where the hell is it going wrong? And this is just a pipeline it's very easy to actually introspect. So this is kind of the second half of the presentation. I'm good on time. That looks good. So I'm going to share a different tab now. Okay, can folks see this terminal? Let me see if I can blow this up a little bit. So the idea is let's start off with a simple C program here. Maybe some syntax highlighting would be nice. So does anyone want to unmute themselves and kind of, talk out, this C code as written by a human is a little bit inefficient. Does anyone spot maybe an optimization or two or more that they can think of that, would be nice to apply to this C code?
We could backwards iterate, save ourselves a register.
Yep, I like that. What else can we do?
Can just fill the entire array with x plus y, whatever that is.
How are we going to do that?
Change.
What optimizations are going to help with that?
Well, just move the x plus y up at the top, and then just replace it.
So code motion.
SSA, yeah.
Yep. Is there anything else that we can think of?
Ain't unrolling.
Cool. Perfect. Okay, so those were the two that I was thinking of. Let's go through and see how does LLVM optimize this function, right?
I'm guessing LLVM will probably just do the x plus y and then call memset That's my guess.
Well, let's take a look. Let's see. So kind of the first thing I'm going to do is I'm going to emit LLVM IR. So this is kind of a big command line. Let's walk through it. So I'm going to tell Clang, I'm going to say, I would like you to produce LLVM IR for me. By default, LLVM's IR can be serialized to disk in either a human readable format or a space efficient binary encoding. So we're going to say -S when mixed with emit LLVM is going to say emit the human readable format rather than the machine efficient encoding. From there, I'm going to, this is kind of messy, but this is, the incantation I need that says, I want you to emit IR that has not been optimized from the middle end. And I kind of need to mix these together because if I don't specify an optimization level, or if I say, 0, Clang's actually going to mark all functions in the IR as like, please don't ever optimize these. And it makes it a little hard to then manually run the passes themselves. I'm going to say, I don't really care about debug info for the purposes of this demo. This cleans up the IR a little bit, not super important. This is a LLVM specific flag that's going to say, keep the identifiers I used in my source code because it makes it a little bit easier to like match up mentally what variables there are. Otherwise, local variables whose names aren't really important, they're not going to be visible symbols, may just get lowered to numbers. Not super helpful. Right. So let's run this. And the idea now is this produced a file called foo.ll. So let's take a look at what this looks like. So this is unoptimized LLVM IR. So right away you see the data layout. Remember I talked about that, and the target triple is kind of the machine that I'm talking about targeting. Which this target triple, which actually has 4 items in it, but it's called a triple. This kind of defines an ABI, or at least part of the ABI. The data layout is actually like way more specific about some things, right? But you can see like F80 is telling you something about long doubles, and it talks about endianness, and I don't know, I can't decode this string by eye, but you can see here we have a function here called foo. It's allocating a bunch of things on the stack here. It's storing some stuff, some bitcast. There's lifetime information about some variables. There's a store. There's a branch to the beginning of the for loop. In the loop, we do, some load, some comparison, and then a branch either into the body of the for loop or some kind of cleanup routine. The cleanup routine, I don't know what it's doing here. It created a bitcast and then marks the end of its lifetime. So that seemed like a waste. I don't know. Like this isn't meant to be efficient IR. This is AST walk, right? Jump to the end of the for loop. So the body of the for loop here, right? We can see, load 2 things that we had spilled to the stack previously. And then here's the add. We're saying, load X, load Y, add them together. Here we do some calculations based on the address where we want to store stuff. And then we do the store of the result of the add into that address. And then we branch to the increment of the for loop. So this is kind of a canonicalized for loop representation in LLVM. You can see here, we load our iteration variable. We add 1 to it, we increment it, we store it back, and then we branch back to the condition. In the condition, right, is we do another comparison and the jump, right? So this is the body of the loop. And at some point we decide in the when we do our condition to branch to the let's see, the cleanup jumps eventually to the end, right? So it's not super efficient. There's all kinds of like attributes and stuff about type-based alias and information, and some information about the machine, and stuff. A lot of like function level attributes will get added here and stuff. Yeah, so time check, we're doing great. We're way ahead of schedule. I'm happy with that. Cool. All right, so that we've kind of generated. We've kind of cut the pipeline off at the knees before the middle end has run and optimized these. So let's say, so Alex, you mentioned loop invariant code motion. Well, let's say I want to run just the loop invariant code motion pass on this file. Well, what we can do is, let me write this to foo.victim.ll. Boom. So if we take a look at this file, we'll notice, it's still very inefficient. The entry is doing all kinds of like loads and stores and conditions and cleanup. But if you remember what the for loop body looked like before, you'll notice now it's significantly shorter. So if we take a look at that real quick, if we say foo.ll and we go down to the for body, you can see here that there's kind of multiple instructions, right? Where we kind of load X, load Y, add the results, and store. Do we do a store? I don't know. The rest of this is calculating information about the index into the array that we're going to write it. Now, if we go back to
store on 38.
What?
38 line 38 had a store.
Ah, good. Yeah, that was a store into the array. Here, if we take a look in the for body, after loop invariant code motion, we can see there is no addition being performed in the body of the loop. Instead, if we go back up to the entry of the function and we look for add, boom, here's the add being done here. And actually part of the address calculation got hoisted up as well. But you can see here now, all we do is basically figure out, where should we be writing into the array and just store the address, the result of the addition into that address. So essentially, this is like much more efficient, but at least only loop invariant code motion has been done. There's more we can do. There's more we can do here, right? So let's take a look now. If we were to run basically every let's run every pass on. I don't want to print all of them. Let's run every pass on this file and take a look at what it looks like. So we'll write this out to foo.opt.ll. Is there anything else we want? I think that's good. Oh, didn't give it input, of course. So we're going to take kind of the output from Clang. So forget the loop invariant code motion thing for a second. Let's just see, what does the ultimate optimized IR look like for this? So that's not right. We want foo dot, and sorry, we want to emit that as human readable, not the binary format. So we use -s. Then we can open it up. Okay, so can anyone see what's going on here? So it's a little bit tricky, and I'm going to walk you through it.
Unrolled a whole bunch.
Yep. So it unrolled the loop fully, and it unrolled it 25 times.
It looks like it vectorized it also.
It vectorized it. So you can see here, there's once up front. So what it's doing is it's basically, it performs the add, and then it does a scatter operation to scatter this into a SIMD vector. And then it's basically doing a bunch of SIMD stores. So it was a good guess about memcopy, but it depends on kind of the size of the machine we're targeting. Like in kind of scheduling, we may decide to lower this maybe in the back end or something to a call to memcopy, versus like SIMD kind of thing. And so, there's kind of trade-offs there. There's issues around, are the operands aligned or not? A lot of things go into this, but essentially LLVM unrolled the loop 25 times and is using a 4 wide vector of 32-bit integers to do these stores. So, if we actually checked that, like if we passed along the size of the array and, checked that it was safe to write all these, that might be better. But, because we didn't, it's undefined behavior to write past the end of the array. So we assume, whatever, just unroll the loop fully, kind of go for it, right? So that's pretty good. But let's actually manually invoke the backend now and take a look at, what actually assembly code gets produced. Actually,
does the middle optimizer pass know anything about the ultimate target? So I guess what I'm wondering is, why did it choose to use 8 wide SIMD vectors when I think Intel can do it, or sorry, it did 4 wide, but I think Intel at least can do at least 8 and maybe even 16 at this point.
I don't know, and there may be a pass in the back end that unrolls it further, kind of thing. So there's a generic loop vectorizer, and then I assume with target information, the loop vectorizer may actually use target-specific information to decide how best to represent a vectorized loop, but it's something I'm not super familiar with. One thing I wanted to show is actually, let's take a look at what are all the passes that get run as part of the middle end. So this little incantation here, what I did basically is I can say print after all. I can say dash print after equals lickum, like whatever the name of the pass is. And I'm just grepping here. It's going to dump the full LLVM IR every time, but I just am grepping for kind of a print statement that tells me what pass is being run. So there's a lot of acronyms here. Can anyone call out maybe some that they recognize?
CSE is common sub-expression elimination, I think.
Yep. Anyone know what SROA is?
Scalar replacement of aggregates.
Good. Let's see. So here we try to infer function attributes, right? There's things that you can't express in C, but if we have visibility into the definition of a function, we can actually deduce more information to generate better code about it. Constant propagation. Let's see, what are some of the other ones I recognize? Mem to reg, right, is, maybe we don't need to be constantly storing and reloading things, but maybe we can try to keep values live across basic branches. Redundant instructions. So like, what are some other ones? Jump threading. Basically, this is the full loop. Rotate loops. We'll try to canonicalize loops instead of looking for every possible way a program can loop. If you have a canonical loop form, it makes it a lot simpler that all passes only need to operate on a specific formation of loops. So LLVM will try to transform, for loops and while loops. Like Chris talked about, maybe iterating backwards is nice when possible, right? That's something loop rotation might do. Loop on switching might try to reorder, if you have nested loops, what order the nesting occurs at. Go ahead, whoever was about to talk.
Yeah, so I was wondering what the canonical loop form for LLVM was.
Good question. That's, I think it's documented, and I recommend going to check for it. Okay. I think the for loop I showed you earlier is kind of the hint at it, but there may be a more specific definition you're looking for.
Okay. I just remember in like the compiler course I took in undergrad, it was everything turns into do while loops. And so I was wondering if that was true in LLVM. So.
I don't know. At the end of the day, everything's going to get lowered to jumps, which are basically go-tos. Whether that's in a structured form, equivalent to a do while, and at what point, it's hard to say. I don't know enough about kind of the loop specific optimizations to have an informed answer for that. Sorry. But we can see here, dead loops we can determine are statically dead. Unroll loops. Global value numbering is a way of simplifying common sub-expressions, I believe. I don't know what LCSSA. It's just a verifier. Is loop contained SSA, I think. Oh no, loop closed.
Loop closed, yeah.
Yep. Loop invariant code motion we can see got run here. I think it actually gets run more than once. We'll see if we see it again. Another DCE pass. It's very common to, after you do some destructive transform, you don't actually do all the cleanups. Instead, you kind of defer to DCE and you just run it afterwards. And so, DCE gets run a lot. It's a trade-off between, if you run this pass and then that pass, or you flip the ordering, they're non-commutative, so you don't get the same results necessarily. So theoretically, you could run DCE after every freaking pass, and maybe it cleans things up, but maybe it's not the most efficient use of compile times. Lower float to int. Maybe there's cases where we can determine you don't actually need increased precision. There's parts of LLVM that are now taking a look at doing optimizations, figuring out which individual bits are actually required for certain calculations. John Reger has blog posts and talks about this you can take a look at. loop rotation, I think we talked about, is a bunch of these probably are getting run again. Yeah. Yep. And so there's verification passes as well. The IR has various invariants, and we want to make sure that no pass violates those, or we want to catch those violated invariants as soon as possible, because those typically lead to code gen bugs. Cool. So now let's take a look at the back end. So
this presumably is parameterized to some extent by the source language rules as well, or?
Yes. So what happens actually, so the tool I'm running for the front end and the back end is opt and LLC, which are generic command line utilities from LLVM used heavily throughout the test suite, but they're just for manually invoking specific passes. For actual language front ends, they will specify a pipeline of what machine independent pipelines they want, and then what backend specific pipelines they want.
Okay, but something like expression reassociation, if I remember correctly, the rules vary from language to language, right? So some of these things are presumably parameterized.
Right. So either the front end can choose either to not invoke these, or the pass itself may take a look at some information to say, like, I'm not valid to run here, just return early, I'm done. Kind of thing.
Okay.
So there's passes in tree that don't get invoked by Clang ever, but maybe they do by Julia, or maybe they do by Rust, or maybe they do by Swift. Kind of thing. So the idea is, if you have all these in one place, you kind of have compiler Legos that you can play with to build, your kind of compiler, right? So let's take a look at the back end.
Can I ask another question?
Oh yeah, go for it.
So if let's say loop invariant code motion does something to one function but doesn't to another, and that invalidates some existing analysis, will LLVM only run it on the one that was changed by the previous pass, or will it rerun it on all of the existing code in the module?
So nothing gets rerun. It basically says, like, if it's basically a way of it's a way of like memoizing the analyses, right? It's like the analyses are heavyweight, and we don't want to recompute them if we don't need to. So it's a way of creating a pipeline and then having that cache be invalidated manually by the pass manager. Basically, it figures out.
So like if the cache is invalidated and then another pass asks for that data, it will on demand generate the analysis?
That's my understanding. Yes.
Okay, cool.
Cool. Let's take a look at the back end. I'm not going to generate any machine code, any objects. Instead, I'm going to generate some assembly code, and we'll take a look. Right.
You're at about 45 minutes too, Nick. Just time check.
Cool. Thanks. So I did not want to print it. I did not want to print it after all. Sorry. So let's take a look at the assembly foo.s. So here we can see, the assembly of our function foo. Right. We have a symbol with global visibility called foo. It does an add, based on X and Y from our calling convention. It moves these into a XMM register, one of the SIMD registers. What the shuffle here is, so we moved it into the first lane. This broadcasts it to all lanes. And then we basically write this to memory 25 times and return. So that was our function. And, we determined for some reason, 4-wide SIMD was the best way to do this, whatever, I don't know. And then same thing, we can print after all. And sorry, I want to pipe this through grep. And here are some backend stuff. So speak up if you recognize any of these, but from the beginning, we'll take a look at, so a bunch of these are still on LLVM IR. And if I spot, there's post finalize ISL. So here at the finalize ISL stage, this is basically instruction selection. Is very big pass, itself a very complex beast. But at this point now we're in mirror land. Tail duplication, if conversion, combine instructions together, kind of classical well, I guess they're more machine specific at this point, but compiler optimizations, eliminate obviously dead instructions. This is where you start to see more backend specific things, right? The LEA is like this God operand operation in x86 where like you can do multiplication with it and like a bunch of things, right? So, convert things to LEAs and whatever, things that depend on implicit E flags. And from here, there's actually a grouping of these is actually the register allocator, right? So these are kind of interesting. 2 address instruction passes. We want to try to, in Mirror, we want to try to use 3 address instructions instead of 2. So there's some tricky stuff we do there. Instruction scheduling, kind of the pre-RA scheduling. Here these kind of work, I guess these work together as register allocation. Stack slot coloring kind of does too. I guess, some group of these tries to figure out, like for the greedy register allocator, what's the liveness of variables, the live ranges of them, color stack slots, and allocate them to physical registers. Tail duplication is like you actually copy code into both ends of a if-then statement if it's deemed to be a speed up or whatever. Actually lets you do tail folding. No, there's some branch folding pass later that depends on this. But eventually, like F entry calls for instrumentation, X-ray, like things we're not doing. The pass runs and says, I don't have anything to do, returns early. Where was it? I don't see it now, but at some point we inserted the function prologue and epilogue. Prologue epilogue insertion is what the pass was called. Prologue epilogue insertion, right? So, if you need to realign your stack to 16 bytes on x86, so you can use stack line operands for SIMD, right? And yeah, so that's kind of an example. And this is kind of where I wanted to stop for questions. So yeah, that's everything that I have. Cool. Does anyone have any questions about LLVM, the architecture, or various aspects of it? And if there's other people on the call that know these things about LLVM, feel free to chime in as well.
Just a comment. It seemed to me that the reason you were getting 4 white vector instructions probably had to do with the default architecture target, right? It was maximize compatibility with old implementations.
Sure. Let me play around with if I set -m arch equals native, let's see what happens, right? Because the base ISA with no instructions extensions to the ISA has SSE2, which is kind of 4 wide SIMD. So we go back to Clang, and I say -m arch equals native, and then we rerun opt. Boom, we got 8 wide SIMD, right? You can see here that we're using 8 wide, 8 by 32-bit.
And that's because LLVM's native vectors are parameterized, right? They're not fixed with vectors, they're arbitrary.
They have to be fixed with, and MLIR makes it so that arbitrary dimensions can be unknown.
Right, so I meant that they're polymorphic types or parametric types. They're not just vector 12 or vector 4. They're vector of some width, right?
Yes.
Okay. Right. Yeah. LLVM IR has support for arbitrary vector sizes, but then whether or not that's legal for your target is different.
Right.
So here you can see we're using a YMM register I think it's SSE4. I don't know if it's actually an AVX register. Let's see, what is YMM? Oh God, YMM x86. AVX, okay. Yeah, so YMM were added as part of the AVX extensions. They support 8 32-bit single precision floating point numbers or 4 64-bit double precision floating point numbers. Maybe if my host I'm targeting should have support for, AVX2 and AVX512. Maybe there was a trade-off there where LLVM decided not to use those. Don't know, kind of thing.
Do you think it looks at trying to find a common divisor between the number of loop unrolls and the vector size so that you don't end up having to do a tail?
And
if it did that, it would.
Sorry, go ahead, Alex.
If it did that, it would need to use 4. 8 doesn't divide 100.
You're right.
So we could take a look at the output. Maybe you might do software pipelining, and it might do something where it sets up the first few iterations of the loop or the last few iterations of the loop to kind of handle that.
And it could use a smaller register to handle the tail.
Yep.
So use 8s and then 4 to get the last 4.
Yeah, so you can see here it does this for the tail, right? Is it just lowers to 4 moves, right? Because 8 into 100 is, I guess, 96, and then are these the 4?
Yep.
Yeah. That is sort of.
You could also have picked 8 only for alignment reasons. Anything larger might have required stricter alignment.
Mm-hmm.
Because your incoming array was, just an integer array.
And typically LLVM will have debug flags. So for instance, I ran LLVM, loop invariant code motion, but there's additional flags I can pass that say print out debug statements that people have inserted previously. So for instance, right now I'm looking into a bug in LLVM's register allocator. And so, the way I'm debugging this is I'm literally invoking LLC because register allocation is part of the backend. And I'm passing a whole bunch of flags that turn on, debug print statements for the greedy register allocator and, where we calculate, where we insert inline spills and debug information about, how we calculate live ranges and things like that. So, it's very nice. LLVM's very easy to work with. It's very easy to introspect, what's going on and where and how decisions were made kind of thing.
So one of the things that I found really useful when working on Clang was just the AST printer that would just dump the AST to the terminal.
Yep.
Now, I was only working on LLVM for a little while, so you definitely have more experience there. Is that something you still find useful? I didn't know the name of all the C++ AST nodes. And so being able to just feed it a file and see the AST nodes was really helpful.
Yeah, so I don't fucking name wrong, but sorry, I have it. The slides that the talk is from, I have the invocation from. Isn't that dump AST? Oh, because I think I need to do this. AST, is it AST dump? Sorry, let me pull up my slides here because I'm mixing this up. But basically the talk that these slides are kind of pulled from, I have kind of the generic ones. Let me just share this tab because, here's the output. Oh, fuck, X Clang, of course. So this is literally like, let me punch this, back into my terminal here. And I'll share it again. Oh, shit. Oops. Present. Not that. Chrome tab. There we go. Okay, so basically, yay, fun colors. This is what the AST nodes look like after kind of parsing an AST construction. There's actually a bunch of implicit things that get defined, like what a _128 is, and weird things that we probably shouldn't be, like an NS constant string tag, which sounds very Objective-C specific to me. Like VA list tags, I don't know. From here, there's type defs so in my example, I pound included std def. Std def only declares like 3 or 4 things. There's actually not a lot in it, but it declares pointer diff as a type diff to long, size t, wchar t, right? So those came from our header. And then from here, here's the AST of, and I guess max align t is defined there as well. Then in my source file, I have a function declaration of function name foo. parameters A, X, and Y. We have a compound statement, right? Block statement. We have a for statement. The for statement, has a bunch of things. This looks like a bug to me. I don't know what the fuck that is. We have, part of the conditional check, are we less than, right, is that, yeah, and then here's the increment. Binary operator is our assignment. We have another binary operator that's our addition of X and Y. And here we're storing, A is the left-hand side of the assignment kind of thing. Yeah, so there's a bunch of, there's general debug, compiler generic debug flags like -E, -E, -S, -lowercase c. There's Clang specific ones like -X Clang dump AST and emit LLVM and stuff like that.
But the null is not necessarily wrong. That's just like a optional, probably part of a for statement. So like if you look there at like the nodes hanging off of like for statement, there's basically things that are in each of the semicolon terminated parts of the for statement, and then so like there's like the loop body and the like the conditions that you're checking, and then the post operations that you have there, right? Like pre operations, like so the null part is probably just some other like thing that can be present in a kind of loop, and they leave it there just in case.
Yeah, I mean, it could be something from Objective-C or something, but I've highlighted an interesting node here, something I didn't write in my source code. Can anyone tell me or guess at this node that I've highlighted right here? Based on the name, what do you think is going on here?
The bane of my existence. Oh my God, the number of implicit casts. They're everywhere in the compiler.
So this is part of the language, right? Like people like to give JavaScript a lot of shit for having implicit conversions, but the thing that a lot of people maybe might not understand is that actually C and C++ are full of the same type of implicit conversions and promotions as well. And there's actually very tricky rules for that are very error prone and actually hard to remember. Something I don't like. They're trying to help with ergonomics, but actually in Clang and LLVM, the implicit casts are actually inserted into the AST at parse time, and that's actually how they're handled in Clang.
Yeah, this is actually a great way to like learn, like when you have something like and you're trying to understand like how it's actually getting cast, like or becoming the proper type, or making sure it's the proper type that you thought it was going to be. Particularly if you have something with like auto, you can use this to like dumping the AST to get that information.
The thing that I use this for was when I was writing my tree AST walker. You have to say on what nodes you do what, and I didn't know that some of those nodes were going to be in there, and so being able to actually feed the code in and then look at the names. And it's also nice that all the line number and column stuff's in there, so it's really easy to trace this stuff back.
Yep, that's all attached to the tokens. The hard part is just not destroying it destructively in your transforms. So that way you can emit proper debug info, which is a whole other trick. So I'm sorry, I've got to run. If you have other questions, I'd love for you to ping me on chat and we can follow up kind of thing or anything. And if you have feedback, let me know. Thanks everyone for tuning in your questions. I appreciate it.
Thank you.
Yeah, thank you, Nick.
See ya.
I'll put this on a G drive.
Appreciate it. Thanks, Alex.